All right, welcome back. So let's do some examples. So first of all, let's look at the following graph. So this is going to be the graph of, or a sketch of the graph of f of x equals x cubed minus 3x squared. And this graph kind of looks like this. It goes up, down, and I messed it up. Up, down, and back up. Okay, and it has intercept, x-intercept at 3 and at 0. Now you see these values, so from this picture we will see this value here and this value here. This is the point 0, 0 in the origin, and this is going to be the point it's minus 4. This is going to be the point 2, negative 4. Okay, so this function has what we call a relative maximum. So this function f has a relative maximum at the point 0, 0. That's this piece right here. Further, f has a relative minimum at the point 2, minus 4. That's this point right here. The reason why we call this relative maximum and relative minimum is because these functions go on forever. This function is defined on the open interval, minus infinity to plus infinity. It's the whole x-axis. You could plug in any x value you want and you will have an output. However, because you could plug in any value you want, as x gets bigger, as x goes to infinity, this implies that y goes also to infinity, because notice that it's going up from left to right. Okay, so as x gets big from left to right, y is also going big. And as x gets small from left to right, y is getting smaller. So you cannot actually find a maximum or a minimum, like an absolute max or an absolute min. You can only find these localized max and minimums. So this max and min, so let's say this is minus 1. This is a local maximum at 0, 0, and a local minimum at 2, negative 4. Or relative max, relative min. Okay. Now, for functions that are continuous, informally we say that the relative maximum, you could have more than one. Sometimes you have two hills that are the same size. The relative maximum occurs on a hill. It kind of looks like a hill. You go up a hill. And the relative minimum occurs in a valley. It occurs on a valley. So informally, this is the way that you're supposed to think about this. You're supposed to think about the relative max as happening when you have hills, and the relative minimum when you have valleys for continuous functions. Now, if the hill or the valley is smooth, then Then the graph has a horizontal tangent line at the maximum or minimum. So at the relative max or relative min. This is going to be important later on in a few minutes. Now, if the hill or the valley are sharp, note if the hill or valley are sharp, then the function is not differentiable. At the high point or low point. So in the case of, for example, in the case of y equals absolute value of x, we saw this a while back. This function, although it's continuous, is not differentiable at the origin because it has a sharp turn. So this will not be differentiable at 0. Okay? Right, so let me define now relative extrema, and then we will see some examples. Right, so let me fix my computer. Right, so this for relative extrema. Number one, if there is an open interval containing C on which f of C is a maximum, then f of C is called a relative maximum. Of f. Or you can also say f has a relative maximum at C, f of C. Okay. Similarly, if there is an open interval containing C on which f of C is a minimum, then f of C is called a relative minimum. Relative minimum of f. Or you can say f has a relative minimum at C, f of C. Okay? Now, the plural, so sometimes you may see this when you're reading books or when you're working with problems. So the plural of relative maximum is relative maxima, and the plural of relative minimum is relative minima. Okay? Sometimes, again, they're called local max and local mins. So I think I used that term earlier. So, you know, note sometimes relative max and min are called local max or min. Okay? All right, so let's look at an example. Let's look at an example. Let's say we're given the following function. And we're given something that looks like this. And we are told that this point right up here is the relative maximum at 3, 2. All right? So this is the local max, 3, 2. We are also told that the function, so this is f of x, we're told that f of x is equal to 9 times x squared minus 3 divided by x cubed. And the question is to find the value of the derivative at the relative extremum value. So the question is find the value of the derivative at the relative extreme value. Okay? Well, I have a function. I'm given f of x equals 9 times x squared minus 3 divided by x cubed, and I'm given a point. The point that I'm given is 3, 1. So I have to find out what the value of the derivative is at 3. So basically I have to find out what f prime of 3 is. Okay? Well, I have a function here. I have a quotient. So I have to use the quotient rule. So by now you should know that the quotient rule, f times g, is going to be g times f prime minus f times g prime divided by g squared. Okay, by now you should know that. You should have that memorized. Anyway, let's let f be the top function. So it's going to be, and you could, you know, we don't need to worry about the 9. We could leave the 9 on the outside. So I'm actually going to leave it on the outside. I'm just going to say that the top function is x squared minus 3. And then the bottom function g is just x cubed. So we have f prime is equal to the derivative of x squared minus 3, which is just 2x. And then g prime is the derivative of 3 of x squared, which is just 3x squared. Of x cubed is 3x squared. And again, I'm leaving the 9 on the outside because of the constant multiple rule. So that means that f prime of x is equal to 9, because I left it on the outside, times g times f prime, so that's x cubed times 2x, minus g prime times f, which is x squared minus 3, all divided by g prime, which is x cubed squared. Not by g prime, all divided by g squared. Okay? So this is equal to what? So we have x cubed times 2x, that's going to be equal to 2x to the 4, minus I have 3x squared times x squared, that's 3x to the 4, and then minus 3x squared times minus 3, that's going to be equal to plus 9x squared, all divided by x to the 6. And now we have to evaluate this derivative at 3. So we have to plug in 3 wherever we see an x. So we have 9 times 2, 3 to the 4, minus 3 times 3 to the 4, plus 9 times 3 squared. all divided by 3 to the 6. Well, let's see what we get. So we have 9 times 2 times 3 to the 4 minus 3 times 3 to the 4. So what I'm going to do here is notice that I have 2 times 3 to the 4 minus 3 times 3 to the 4. So it's going to be minus simply 3 to the 4. So I have 2 of them minus 3 of them. It's going to be minus 1 of them. So it's going to be minus 3 to the 4 plus 9 times 3 to the 2. But notice 9 I could rewrite. So 9 is the same thing as 3 squared. So this is 3 squared times 3 squared, really, what I have here, over 3 to the 6. But 3 squared times 3 squared is simply equal to minus 3 to the 4 plus 3 to the 4 divided by 3 to the 6. Because we rewrote 9 as 3 squared. But now, negative 3 to the 4 plus 3 to the 4 is 0. So we have 9 times 0 over 3 to the 6. But 0 divided by 3 to the 6 is 0. And then 0 times 9 is 0. So we have this whole thing is equal to 0. So we have that f prime evaluated at 3 is actually equal to 0. Okay? All right, so that's the first example. So we found out that the derivative of this function evaluated at the maximum, at the relative maximum, is equal to 0. Let's do one more. So let's do another example. It's going to be a similar problem. We're going to find the derivative at the, in this case, well, at the relative extrema for the given function. The given function is y equals sine of x. If you remember from pre-calc, y equals sine of x looks like this. It goes, and I'm only gonna do it on the interval from 0 to 2 pi. Anyway, it goes from 0 to 1 down to minus 1. Here we have pi. Here we have pi over 2, and here we have 3 pi over 2. Okay, so that means that this maximum right here, this local maximum on this interval, is pi over 2, 1. And this minimum here is 3 pi over 2 minus 1. Okay? So again, we are asked to find the derivative at the relative extrema. So now we have two inputs. We have pi over 2 and 3 pi over 2. And our function is f of x equals sine of x. Well, by now you should know that the derivative of sine is simply cosine of x. And now we just have to find out the value of cosine at pi over 2 and at 3 pi over 2. So if you do f prime at pi over 2, the same thing as cosine of pi over 2. And again, if you remember from pre-calc, cosine begins at 1, goes down to minus 1 between 0 to 2 pi. So at pi over 2 you have 0, at 3 pi over 2 you also have 0, and then at pi you have negative 1. So cosine of pi over 2 is going to be equal to 0. Similarly, again by the graph, cosine of 3 pi over 2, which is the other extrema value, is going to be cosine of 3 pi over 2, which is equal to 0. Now, from these two examples, what I want you to realize is the following. When we take the derivative of a continuous function on an open interval, and we evaluate the derivative at a relative maximum or minimum, or relative minimum. We got the derivative being 0. Equal to 0. Also recall the derivative evaluated at a point x, or at a value, let's call it c, gives us rather the slope of the tangent line at the point C. So since f prime, let me rewrite it. So since the derivative evaluated at a relative max or min, relative min, is 0, this means that the tangent line at these points has slope 0, since again that's what taking the derivative and evaluating at a point meant. Okay, remember when we took the derivative and we evaluated at a particular point, that gave us the slope of the tangent line at that particular point. So because, as we see from these two examples, whenever we take the derivative and we evaluate it at a relative max or min, we have that the derivative is equal to 0. That means that the slope of the derivative at the relative max and min is 0, which means that we have a horizontal line. So that's the big takeaway from this section. Okay, the big takeaway from this section is what I'm going to be writing now in a second as two theorems. So first of all, let me define one thing and let me write down the theorem. But the big idea is what I just wrote up here. So let f be defined at c if the derivative of c is equal to 0, or if f is not differentiable at c, then c is a so-called critical number of f. So again, if the function f is defined at c, meaning that the value of c or f of c exists, if the derivative when you evaluate f at c is equal to 0, or if it's not differentiable at that point, then c, this number c, is called a critical number of f. So what do we mean by f not being differentiable at c? Well, if you have this case, let's say this is c, and c looks like this. That's pretty sharp right there. That's a pretty sharp turn. We know from, again, the example with the absolute value, whenever you have a sharp turn, that means that the derivative does not exist at this point. Okay? Similarly, the other half, if the derivative is equal to 0, then this is what we have. So if you have something like this, so you have a parabola, right? Yeah, it's an ugly looking parabola. Parabola. Then what we have here is, like I was saying, we have a horizontal tangent line at its maximum value, and that maximum value is f prime of c. So this is a horizontal tangent. Okay. And now this leads to the next theorem, which is a very big part of the class and where I'll end this part of the lecture, is the following theorem. This is another very important theorem for those of you who are going to be pursuing bachelor's in mathematics or further education in math. This theorem is the following. If f has a relative minimum or a relative maximum, at x equals c, then c is a critical number of f. Okay. So what this tells us is that whenever we have found the relative maximum or a relative minimum, then we have found a critical value for the function f. We have found points where the tangent line is going to have slope 0, meaning where the tangent line is going to be a horizontal line. And this is going to have some consequences that we will see in the next part of this lecture. Thank you for your time.